In this lesson, we're going to explore correlation in a more analytical approach. We're going to actually calculate the correlation coefficient for a small set of data. So this particular formula is given on your formula sheet in the AP exam. Hopefully this part looks familiar to you. An x minus the mean over the standard deviation. Hopefully that's jumping out at you as a z-score. So R is really calculated using z-scores. So we're going to find a z-score for our x and our y data points, multiply them together, find their sum, and then multiply that by 1 over n minus 1. So let's explore it with this very small list of data. At a quick glance, you could say this looks fairly linear. It's certainly not a very large set of data. Fairly strong linear positive association is what I'm seeing. So I would expect a high R value close to 1. I've listed your ordered pairs in the table, and what I'd like you to do is pause, find your mean and standard deviation for both the X column and the Y column. You are welcome to use your one variable stats for standard deviation if that's quicker than by hand. So here are my results. And now to use the z-score formula, I need to find the z-scores of my x values. So I am going to substitute. So I need to do x minus the mean. So I will do, just grab my pointer tool. I'm going to do 1 minus the mean of 2 divided by the standard deviation. So 1 minus 2 is going to give me -1 divided by 0.816. 2 minus 2 is going to be 0 over 0.816. My next one is the same. And then 3 minus 2 would be 1 divided by 0.816. For the y values, similarly, I'm just using 1 minus 3 this time would be -2 over the standard deviation of the y's would be 2.16. I'm going to get 2 minus, you know what? I'm not even going to bother to calculate that because I can see from the formula I'm going to be multiplying these two columns together, the z-scores of the x and the y. And this right here equals 0, and this equals 0, so who cares what the y equals? It's going to give me 0 anyway. So let's save some time. The bottom one would be 6 minus 3 would be 3 over 2.16. So R is equal to 1 over n minus 1. N is the size of my sample. I've got 4 data points, so this will be 1 over 3. Times sigma. So sigma means I am going to be summing the product of my two columns. So I'm taking this times this, so this row times this row, and this means I'm summing them. So when I take -1 times -2, that would be +2. My denominator for all of these is going to be 0.816 times 2.16, so I'm just going to write that once. And then I jump down to the bottom one. My numerator, 1 times 3 is 3, and I'm going to be finding that sum. So now I have it something very workable that I can toss in my calculator. 1/3 times 5 over that product in the denominator. I get approximately 0.946. I would encourage you to put this data in L1 and L2, which you probably already did for your one variable stat, and run your linear regression, which is stat calc option 8, to see that correlation coefficient, that R value, and hopefully it's very, very close, maybe off by a few decimal places as you get out past the thousandths place. So let's just kind of wrap up everything we know about correlation and the big ideas. So when we interpret R, we always talk direction, which would be positive or negative. We talk form, and it needs to always be linear, and the strength as well. And correlation ranges between -1 and 1. 0 having no correlation, and then weaker to stronger. Of course, you can have moderate in here as well. And we use the ly words for in between, like fairly moderate, fairly strong. Again, strong over here, moderate to weak inside. Now, some other big ideas hopefully came from, some of the other big ideas came from looking at the applets in our last activity. So if you just graph some different points here, you can see the correlation here. You can see it's -1, and here I'm putting them very much in a linear pattern, so it's very, very strong. Now, look what happens if I pull something, an outlier, out of pattern. Look at how much it drops, okay? That correlation majorly dropped. So an outlier out of pattern will really pull that correlation. Now, if I have something like this, again, 1 point down here, look at how much that makes it appear like there is a strong negative association. I'm going to clear it again. Now let's say, here I see somewhat of a fairly moderate correlation. If I have an outlier, this is really far away, but it's still in pattern, it's strengthening that correlation. It went from like 0.8 something all the way up to 0.9. So an outlier in pattern is going to strengthen, an outlier out of pattern will weaken my correlation. And remember that you can have a strong association but no correlation. So right here, I would say that this is really having a strong association. It's nonlinear, which is why it doesn't really make sense to talk correlation here. And you can see strong association, but I'm very close to 0 as far as the correlation. So let's finish with our big ideas regarding correlation. So one of the things that's important is that we're calculating R we saw from our z-scores. So your correlation coefficient does not have units. If we switch x and y, it does not change R. There's no distinction between our explanatory and our response variable. And you saw that with the formula, you're just multiplying the z-scores of the x's and the y's together. So if you flip-flop the two, it's not going to change the value of R by the commutative property. In the applet, we saw that R is not resistant. It is definitely affected by outliers. Our outliers in pattern will strengthen R, whereas outliers out of pattern will weaken our R value. And our final just major concept would be that correlation does not equal, fill in my blank, causation. We examined that by looking at spurious correlations, and we discussed possible lurking variables. So what I want you to do now is complete your guided notes by answering the check your understanding questions. You can certainly pause the video, try them on your own, and then hit play after you've attempted them. So you were asked to interpret the correlation of R equals 0.791. So I glance at the scatter plot first of all, and I just make sure, do we have quantitative data? Is it fairly linear? And do I have any outliers? So I look at this and I check my conditions. So I state there is a moderately strong positive linear association between, put it in context, chocolate consumption and Nobel winners. The next one is really seeing if you understand correlation and causation. If people in the US started eating more chocolate, can we expect more Nobel Prizes to be awarded to residents of the US? Explain. here's one more scenario. I would like you to pause the video, attempt the questions, and then check your answers. I noticed several typos here. So Joan is concerned about the amount of energy she uses to heat her home. The plot, this should say, shows the mean number of cubic feet of gas per day that Joan used each month against the average temperature that month in degrees Fahrenheit. So I definitely have quantitative data. The correlation is negative 0.861. Look again at the scatter plot. So not only do I have quantitative data, it looks fairly linear. This says, explain why it isn't correct to say that the correlation is negative 0.86, and I need to scribble out this A. There's another typo, cubic feet per degree Fahrenheit. Well, correlation is calculated using standardized values, so it does not have units. What would happen to the correlation if the gas consumed was the explanatory variable and the temperature was used as the response variable? So I've stated that the correlation would be the same. R makes no distinction between explanatory and response variables. You can flip-flop the two, recalculate, no difference. And our final question, what would happen to the correlation if the temperature was measured in degrees Celsius rather than Fahrenheit? So hopefully you recognize the correlation would be the same. Since R is calculated using standardized values, changes in the units don't affect correlation. You could also think of it as the distance between the scattered points is going to remain the same, which is why that correlation would be the same.